Hello everyone and welcome back. So today I thought I would do a video on mathematics, or to be more precise, a proof of why the limit of as x tends to 0 of sine x by x we get 1. Now if you've done a calculus course then you must definitely be familiar with this expression over here. I would say that it is the most fundamental trigonometric limit, if not the most popular limit that you find. That is, this expression over here is 1. So as to why it's so fundamental is that most trigonometry problems actually involve you manipulating the expressions within it to simply get this limit over here, and then it involves you substituting the value and getting the answer. So it is actually pretty important. And it turns out that the proof for it is actually quite interesting to go through as well. So I thought that would be the video that I would make today. But before we actually get into the proof, something something that is worth pondering is how one would actually start doing it here. So if you just substitute the values over here, you see sine 0 is 0 and x, if you put x as 0 it will be 0. So sine 0 by 0 is 0 by 0, and it's an indeterminate form. So the first thing that you might think of doing is uh, using the L'Hopital rule and differentiating the numerator and denominator to get cos x by 1, and then substituting cos 0 and you'll get it as 1, and it checks out. But the thing is, the L'Hopital rule is based upon differentiating, and the derivative of sine x will is only possible if you know what this limit over here is. So you cannot use the fact that the derivative of sine x is equal to cos x without actually knowing what the result of this limit over here is. So it's not actually possible to evaluate this limit using the L'Hopital rule. So instead what we have over here is a beautiful proof using the unit circle, which is something that I'll be showing over here. Also, it's a wonder that I've managed to make this circle so cleanly. Anyway, so I'll construct the geometrical figure that's required and I will come back to you in a second. Alright, so this is the figure that we'll be working with over here. Just take a minute and pause the video if you have to take in what exactly I've drawn over here, but I'll also be explaining it as we go along. So what we have over here is a circle of radius 1 unit. You can take any arbitrary radius r, it really doesn't matter to be honest, but I take it as 1 unit just to make it a bit more convenient. So what we're really interested in over here is to find the area of three main shapes or figures in this construction over here. So first what we'll do is we'll find the area of triangle OAC, then we'll find the area of arc OAC. These are not the same because as you can see the arc has just a tiny bit more area, and finally what we'll do is we'll find the area of triangle ODC. So you know what the formula for the area of a triangle is, it's half BH. There are of course other formulas, but we can just use this because it's the most convenient one. So what we'll begin with is finding the area of triangle OAC. Alright. Now we know it's half BH, so in this case the base is actually OC, that is the radius r of the triangle, which is just 1 unit. So what we can do is we can write this as half into OC, so that's OC is just 1, and the height is actually AB. Now what is AB? So since this is actually our radius r, radius r is a OA, and that is actually the hypotenuse of this triangle OAB over here, what we can actually do is we can write OB as OA sine theta, and that is nothing but just sine theta because OA is 1. So what we can do is we can substitute this thing over here and we can write this as sine theta. Of course you would have also got the same thing if you had used the formula half AB sine theta, and since A and B are simply just 1 unit and 1 unit over here, you would have got the area as sine theta by 2 in the other case as well. So what we'll just write this over here is sine theta by 2. So this is our first area. Now our second area is the area of the arc OAC. Alright, so I'll write OAC over here. Okay, OAC. And note that I should have written triangle over here, yeah. Just triangle to denote the fact that it's a triangle, and this thing over here to denote the fact that it is in fact an arc. So the area of that would actually be r square theta by 2. So since we can rationalize this by the fact that the area of a circle is pi r square, and a circle subtends an angle of 2 pi, right? So if I substitute theta as 2 pi, you'll actually get pi r square if I use the formula r square theta by 2. And of course there's a derivation for it as well, but we can just accept it here for now. And again, since r over here is 1, what we can just write this as is theta by 2. Alright. And finally, our third area will be the area of triangle ODC. Alright. So this is in here. What we're going to try and find out is the length of DC. We already know OC is actually 1. And now what we'll consider over here in this case is the same triangle. And in here, CD is actually perpendicular to OC. Now again, we can use our basic trigonometry. We can say OC by OD is actually equal to tan theta. Alright. So what we can write is, oh no, I mean to say OC by CD. Oh my bad. Oh, I selected the areas over there. Yeah. OC by CD is equal to tan theta. Oh my god, you must think I'm okay. It's actually CD by OC. Yeah, I'm just my bad. So yeah, so CD by OC is tan theta. So CD is actually equal to OC tan theta, and since OC is 1, we can just write CD is equal to tan theta. And so CD, the area of triangle ODC, is actually equal to tan theta by 2. Alright. Now what we want to do next is to find a relation between these three areas. Now by simply looking at the figure, you can clearly see that the area of triangle OAC is lesser than the area of arc OAC, which is lesser than the area of triangle ODC. So that's what we'll write next. We can say sine theta by 2. Remember, this is sine theta by 2, not sine of theta by 2. Is lesser than theta by 2, and this again is lesser than tan theta. Alright. Now another thing to note is the fact that if we make this theta as small as we keep on making this theta smaller and smaller and smaller, what we'll find is that these areas actually become equal. Oh yes, tan theta by 2. So what we'll do is we'll actually put this slack and the slack inequality over here to show the fact that these areas can actually be equal when theta is 0. So of course when theta is 0 there's no area, but we just imagine it as small as we can, the angle that we have over here, so such that these will become equal at some point. Now since theta, we're considering theta as positive over here, we can just do the cut like this. I mean, yeah, we don't need theta to be cut or positive over here, we can just cut 2 anyway. So what we'll do next is we'll do sine theta by theta, and we'll actually write this as sine theta by cos theta. Alright. So what we're going to do next is actually we're going to cut sine theta in all the places, and we're going to divide this by sine theta over here. Alright. And so now you can see that we're getting closer to our answer here. And yeah, we can cut sine theta over here because theta is greater than 0, and if theta wasn't greater than 0, then we'd have to do it in 2 separate cases, but since theta is greater than 0, you can simply cut it over like this. What we're going to do next is we're going to take the reciprocal. Now when you take the reciprocal, you know that the inequalities will get switched. So I will have to do next is actually write it like this: 1 is greater than equal to sine theta by theta, and this is greater than equal to cos theta. Alright, so now we have almost gotten to our answer. What we need to do next is apply the squeeze theorem, which says that if we have an expression of this form, that is, we have an expression that is squashed between two separate expressions, and if we take the limit and we find that this limit and this limit are actually equal, this limit will be equal to the same limit. And I know I didn't do a great job of explaining it, but if I would express it mathematically, what it says is basically if I apply the limit, suppose is theta is tends to 0 on all the sides, on all the expressions, limit as theta tends to 0 of sine theta by theta is greater than equal to limit as theta tends to 0 of cos theta. So to reiterate, what the squeeze theorem says that we know the value of this limit over here and we know the value of this limit over here. So what the squeeze theorem states that the value of this limit will actually be equal to the value of this limit and the value of this limit. You can probably look it up on Wikipedia because I've not done a good job explaining it. Maybe I will do another video on this explaining it better. But anyway, our conclusion is the fact that limit as theta tends to 0 of sine theta by theta is actually equal to 1 by the squeeze theorem. So this was our whole proof over here. It's really wonderful how just through a circle you can get a limit which I believe is actually the most popular limit as far as limits go. And thank you for watching and see you next time.